a special talk starting a sequence of events throughout the week, which will focus on telescopes. Telescopes as we know it, as things which enhance our vision of the universe. And particularly these telescopes that we'll be talking about are telescopes that are using light which even our eyes can see, because there are other kinds of light and there are other kinds of telescopes which see that kind of light. But here it's going to be more between us, things that we relate to, that we can see ourselves. So the series of events begins with this talk which I, Samir Durde, have put together. It's a talk about the large telescopes of the world. And I know many of you, even the children in fact, are very interested in records. So what is the largest, biggest, farthest, tallest? Such kinds of records excite us. And so if you are excited by such things, this is the perfect talk to listen to in terms of, in the context of astronomy and telescopes. So do you like to know about large telescopes? Of course, so that's why you're here. This special exhibition which is going on, Vigyan Samagam, it has a range of mega projects which are being highlighted, and you can see some of them, most of them named here. And they, this picture will show you that they range in what they cover from directly from the early universe to things which we know now, which are the planets, etc. Right? You can also see them here if you're closer by. So all these things are up there in space, and they are being covered by some or the other project. And you will notice in between here there is something called the TMT. Okay? And that is the 30-meter telescope. So this talk is coming to you courtesy the 30-meter telescope project, which India is a part of. I will of course not jump into what is 30-meter telescope, etc. right away. One way to get some bit of information is through my talk, and the other more detailed information can be had at the actual exhibition in the panels. So there's a enthusiastic set of volunteers waiting there to tell you details and show you a model also of the telescope. But before we get into that, before we get into all that, let us quickly look at what is a telescope, and in very simple words try to understand what the purpose is and why people have been using them. So a telescope is, we all know, it's made to look at distant objects. But what does it do especially? It makes things bigger, brighter, and sharper compared to what our eyes can show us. Okay? We look at same things. In fact, there are things like stars, etc. in the sky, planets. There are 5 planets, bright planets, which can be seen with the naked eye. Has any of you seen a planet in the sky by yourself without a telescope? You haven't? So you have. If you guys haven't seen any planets, you can come closer. It'll be nicer to see. Come here. Yeah, kids, you can come this side. We are just starting the talk, and it's about large telescopes of the world. Get inside. You can give some space. All right, lovely. So we are looking at the aim of a telescope, which I am saying is this. But the first question that I'm asking is, has any of you seen a planet yourself in the sky? Okay, we have seen the sun, the moon, stars. Has any of you seen a planet? Do you want to see a planet? All right. So all you have to do is today evening go out and look up at a place where there's no buildings and trees, if possible to find in the city. Just look upwards. One of the brightest objects in the sky, which look like a star, is Jupiter. It's the planet Jupiter. Okay. It is present in the sky even today, but later in the evening. All right. So around 8 o'clock, if you go up, on your roof or in some ground close by or some open space, look upwards, you'll find a bright shining object, which is Jupiter, the planet Jupiter. Okay, so it is there in the sky. And so hopefully that inspires you to look for more planets. So later in the night we can see Saturn. Earlier in the morning we'll be able to see Venus also. Okay, Mars is also there. So there are 5 planets which are visible with the naked eye. Okay, and it's not visible just to me. They've been visible forever, always. Okay, all human beings who used to care for nature rather than TV and internet before, they used to know about planets because in the evening there would be no TV to watch. So the best channel to watch was the sky channel, right, up there in the sky. So they would watch it and they would know that these are things, these bright things, they change their position compared to other stars, right? Stars could be seen, planets could also be seen. However, how many thousand years can you just keep track of planets? You have to do something new, right? Okay. So people said, okay, fine, I know everything, I know how they move, I have detailed records of them, I can predict where they will be 100 years later. Okay, some people even started a business called astrology with that, but they had nothing more to do. They said, no, I need something more, I need to see these better. Okay, I cannot just stop at knowing that there are dot objects moving in the sky. Why do they move? What is special about them? All these questions led to the use of a telescope for astronomy. Okay, so astronomy is also, even if you look at Jupiter with your naked eye, take recordings, look at the moon, sun, etc., it's also astronomy. But the real astronomy of details of things in the sky began with the use of a telescope. And what did we aim to do with the telescope? We aim to make things look bigger, brighter, and sharper. So they should be clear also, right? It should not just be a fuzzy big ball. It should show us details. And just as the picture shows, anybody can use a telescope. So whether you're a small kid, small girl, small boy, old person, middle-aged person like me, who's actually a professional in astronomy, everybody can use telescopes. Only they might be of different kinds. And depending on your purpose, you will use different kind of telescope. So let's look at, there are different types of telescopes. You can see here people doing lots of yoga poses with their telescopes. These are amateur astronomers. So people who are not directly paid for doing astronomy, but they have a hobby, but it's an intense, passionate hobby. So they buy their own telescope, they go out to dark places, set their telescopes up and have a look through them. Okay, and they enjoy looking at it every day. Of course, so the kind of telescopes they use are these kinds. Now here there's a little bit of science, of course, because I cannot do a talk about telescopes without telling you a little bit of science. Any of you want to go into future research in astronomy will definitely have to know about these things. So science cannot be done away with in a science exhibition. So has anybody heard of a term called refraction, which goes into the word refractor? Refraction suna hai? Have you heard? Okay. How about reflection, which goes into the word reflector? Reflection you have seen. Okay. Where have you seen reflections? Right. Every day, brushing your teeth, you see a reflection. Right. Yeah. So reflection is basically the light which is being reflected from your face. It goes onto the mirror, and then it's reflected back into your eyes. Okay. It's just changing the direction. It's not, mirror is not absorbing all the light and then giving it to you like that, right? It's just reflecting it, changing the direction of the light. That's called reflection. Reflection is changing the direction of the light, and there are some laws governing how and which direction will the light go after reflection. Okay? So that's reflection. Refraction is also something we use all the time, but it's not so visible. Reflection is very evident. Okay, I see a mirror, I see my reflection. Refraction is happening right in your eyes. Your eyes have lenses, right? So what's happening in your eyes? So all the light that is coming from everywhere, you're looking at me, the light being reflected off me is getting to your lens first. And this lens is focusing the light onto your retina. which is at the back of your eye, right? So that, what is it doing? It's light coming from all directions, but it's been pointed in one direction, right? So it is also a change of direction, but it is passing through the lens. It's not just being passed off by the lens. Okay? It is passing through the lens. When it passes through the lens, which is not the same as air, its density is different. Okay? It's thicker, it's denser, and so the density being different, the light gets converged and it falls at one point on your retina, and that's how you see sharp focused images. Okay? If people don't have proper eyes, the lenses are defective, we have to wear spectacles because we want to correct for that. What do your spectacles do? Again, refraction. They're changing the light direction slightly so that it's, for your lens, it becomes perfect. Okay, so both of these are change of direction. Both of these can be used to make light go in a certain way. Okay, and this is used by telescope makers. Okay, and so whichever telescope uses more of refraction at the first place. So first time, like I just said, your eyes collect light and then they tell you information about the world, right? So what is the first collector of light? Where is the light passing through? Your lens. Okay, so your eye is therefore a refractor, because the first time light interacts with your eye is through refraction. Okay, but instead of lens, if I had a mirror, it would be called a reflector. But it wouldn't make any sense because light would just go off. I wouldn't see anything in the world. Yeah. So a plain mirror is a reflector. All right. Telescope makers use both of these kinds, and let's see how they use them. Okay. So of course, just to complete the purpose of this slide, let me tell you that there are refractors which use refraction, there are reflectors which use reflection, and there are compound telescopes which use both of them in some way. Okay, which use both reflection and refraction. And they also, of course, if you have a telescope, a small binocular, have you seen binoculars? Okay, have you seen telescopes? Some of you have. In fact, if you say you have seen a binocular, you have actually seen two telescopes, one for each eye. Right? A binocular is actually two telescopes, if you realize that. Yeah? One for each eye, but they are small telescopes. They're compact to stay in your hands. However, if you want better and better view of the sky, what you do is you make bigger telescopes, right? And so as you go and make bigger and bigger telescopes, you can't hold them in your hand, right? So then you have to put them on a particular kind of stand. So people develop various kinds of stand which are called mounts. Okay, mounts like you sit on a horse, it's called mounting a horse. Similarly, you mount a telescope, and the kinds of mounts are something called, this is a technical name, alt-azimuth or equatorial, fork or German equatorial. Okay. Just if you are interested in trivia, this is the kind of, these are the most important kind of telescopes and mounts which are used these days. All right. Now let's look inside them. So refracting telescopes, what do? They basically have the first contact with the light. So this white grayish thing with arrows that you see, let's consider that to be light. Okay, and this is called a ray diagram. Okay, later in physics you may use them. So this is a lens here. It's called a double convex lens. So you see such a shape which is bulging outwards is called a convex shape, right? And this is a double convex, so it is convex on both sides. What this does, it changes the direction of the light and it makes it go and make a point. Okay, all the light is collected at a point. Have you tried sometime mischievously trying to burn some paper with the sunlight using a magnifying glass? Okay, try doing it. Don't burn your house down, but it's not too bad. Yeah, do it at a safe place. It's something you should experience. That's if you do that, you'll realize that that's what is doing the same thing here. It's collecting the light of the sun from the whole surface of area of the lens, and it's collecting it to a point, right? And that makes all the heat concentrated at one point, and so much heat can actually burn paper. Okay, and that's why we say don't look through a telescope towards the sun. because it can actually burn your eyes. Burn, not, I'm not saying figuratively, they can actually, make a dark spot on your eye, right? So we don't look at telescopes, we don't look at the sun with a telescope without a filter. So there are special filters available. So what we are saying here is that if the light comes, a lens can actually make it go towards a point. A lens can also do some other wonderful things. It can make a point which is light coming from a point go in all directions also. It can do the opposite also, right? So what refractors do is, there's a lens which collects it to a point, and then there's another lens which makes it back into this kind of parallel rays. Okay, the other lens is called eyepiece. So you say, what did we gain with this? Right? We made all the light converge to a point, and then we again made it parallel. So kya fayda hua, right? So the advantage here is, you see, if your eye is very small, right? It's less than a centimeter of the area. The diameter of your iris in your eye is less than a centimeter sized. Right? It can collect only limited amount of light. Now what has happened here is, if you use this lens, which could be your favorite size, you could use 1 inch lens, 2 inches lens, 10 centimeter. It's your let's say you choose your favorite size. Okay, you get a funnel kind of an effect, right? You have a narrow mouthed bottle, you want to fill water in it, or you want to, let's say, collect rainwater in a narrow mouthed bottle, right? You take the bottle out, you spend 1 hour and have very little water. But if you take a funnel on it, funnel, okay, put a funnel on it and stand for the same amount of time in the rain, you might be able to completely fill up the bottle, right? What is happening is, all the area of the funnel is collecting water, and then it is putting it directly into the bottle. So this is more like a funnel. So what we have done here is collected light over a large area and then funneled it into a point. But our eyes need to see parallel light, because they also have a lens, right? That also focuses on the retina. So I cannot say that I have collected all the light at this point, now you see what is there, because it's just a point. I'll just see a bright point. So for that light to be seen by our eye, I need another lens which will make it parallel. So this particular lens does not have any too much significance other than making the light parallel again. Okay. There is one significant, of course, point, that the distance between here to this point and the distance between here to this point, the center of the lens to this point and the center of the lens to this point, are called the lens's focal point, focal length. Okay, the point is called focus, and the length is called focal length. Okay, and this is fixed for every lens. So what we have done here is see a perfect alignment. So we have put this lens. The lens focuses the light to this point, and exactly from we have arranged this lens so that its focal length is also at the same point, matching with the same point, right? And then from the focus, the light goes out and it becomes parallel. So this arrangement is called focusing. If you have ever used used your binocular, you see you need to focus a bit. What you are doing is matching the focal lengths so that they come at the same point for both the lenses. Okay, so when you do that, you get a parallel light. But there's one advantage, that if you divide this focal length by this focal length, gives you something called magnification. Your image will turn out to be bigger also. Okay, so that's the second use of an eyepiece. If you're using your eyes to see something, you'll get a bigger image also. Yeah? Size will be bigger inside. Okay, so this is a refracting telescope which uses lenses to converge light, and then an eyepiece to give you a proper image. Right? So we collected light with a lens. We could collect a light with a mirror also. How? People are asking a question, how big can I make a lens? Okay, what is the biggest lens you all have seen? Say, if you have seen a magnifying glass at home, okay, how big was it? Can you show me with your hands? Utna bada hai? Okay, yeah, so this size is good enough. Have you seen a lens this big? No? Why do you think we haven't seen a lens that big? Because see, lenses have to be perfect, right? Especially for astronomy and actually imaging, right? They need to be perfectly shaped, they need to be transparent, they need to be free of bubbles, etc. They can't be like paperweights which have bubbles and colors in them, right? These perfect lenses are very difficult to make. You need to have so much glass, it's got a weight and everything, so they become very costly, right? So it's very rarely that we make big lenses. But now if I ask you, what is the biggest mirror that you have seen? Both mirrors and lenses can change direction of light. What is the biggest mirror that you have seen? Pretty big, right? I've seen, dance floors with, Zumba dance classes, etc. They have walls which are all mirrors, right? So they can be made very big and they're not too costly, right? Of course, if you have a plain mirror, if light comes like that, it goes back in the same direction. You don't want that. You want to focus light, as I just showed you. Then you can use the eyepiece to turn it in, make it turn and go into your eye. So to focus light, people realized that you need to have a concave glass. So a glass which is curved inwards. A mirror which is curved inwards. That can actually focus light. Okay, and if you really want to see a bit more of these things in practice, there is a show happening at 2 p.m. today. It's called an optics show, and we are also going to have Galileo on stage here, who will talk with the demo people, and they will be showing him the modern optics. Why? Because Galileo was the first person to use a telescope like this for astronomy, a refracting telescope. But today, 400 years after 350 years after he is died, we are building huge things, 30-meter telescope, etc. So he comes to this modern age and he wants to know what has been the development, and that's what will be shared through the stage show at 2 p.m. So if you're welcome, if you are here, you're welcome to join us and enjoy that show. So what I was saying is, we use curved mirrors. Okay, so in this one, you'll notice the light comes through and goes to this end of the telescope. It's not at the beginning, it's at the end of the telescope. There's a curved mirror and it is pointing the light in this direction. Of course, if I point it here, I can't put my head there, right? Because all the light will be blocked in that case. So a very clever person, his name was Newton. Have you heard of him? So what he did was he's put a small flat mirror here, small, not of the whole width, small flat mirror here. And what it did was it changed the direction and it made it go in this perpendicular direction. Okay, and then he made a hole in the body of the telescope. Instead of having a hole at the back of the telescope, he made it here and then put the eyepiece lens there, and then he got the image here. Okay, so this is called a Newtonian kind of reflector telescope. Okay, and it's very easy to make these mirrors of big size, and this small mirror hardly makes it of course blocks some light, but it doesn't block all the light. So if we make this mirror big enough compared to this mirror and place them properly, I think we get a very good amount of light compared to a small lens telescope. So you have a question? Submarines, they use periscopes. Yes, they use flat mirrors only to change the direction like this and bring it down. That's right. Yes.
What is the advantage of making?
I can make the mirrors big compared to a lens of the same size. A mirror, it's much less costlier, and they're easy to make even at a bigger size. So we prefer these instead of lenses. Any other questions? Okay, so refraction is clear to you. Refracting telescopes are clear to you. Okay, so we understood something. In fact, I have a demo reflecting telescope here, right? And there is a demo of how to make small telescopes yourself going on at the demo corner in the science center. So if you're going there, we have colleagues there sitting, and after this talk, they will be there. They can tell you how to make them at a low cost. So you don't have to really spend lakhs of rupees on a telescope. How can you do it for a few thousands or even a few hundreds if you are at a school level and you want to make one yourself? Okay, both reflecting and refracting. Go there, have a look, and tell your friends. So reflecting, refracting, and then there's another kind in which basically the light comes like this, and instead of making it go like this, they put another mirror here, and they have to drill a hole in the first mirror and then this light goes through and the eyepiece is kept here. This is a bit more complex, right? But it is also used, and it's called a Cassegrain, or there's also a Gregorian type, as was discovered by somebody called Gregory. Okay, and this is a design by Cassegrain. Okay, so these are kinds of telescopes that I have. Now let's come to the exciting part. Okay, so as I said, I will tell you about records, etc. Right? So what is the biggest refracting telescope in the world? Yeah. The smallest refracting telescope, not smallest, but the first refracting telescope that was made by Galileo. Okay, for astronomy purposes, because other people had made telescopes for other purposes, but Galileo used it for astronomy, and he made it himself. It's important to remember. He actually took a glass piece over time, over many days and weeks. He ground it into a curved lens. Slowly by slowly, he polished it, made it transparent and properly shaped. He had to make a few of them, not just one lens, and then he had to put them together in a tube. But the size of that, okay, the diameter of each of these of the biggest lens in that was around 2 inches in size. Okay, and you will see another small 2-inch telescope at the demo corner also. So you can compare that. Even that is big enough compared to your eye. A 2-inch is an area bigger than your eye. So it will give you some advantage, right? You will see the moon brighter. You might be able to see Jupiter better, but then it won't really give you a huge edge. So you will not be able to see, say, some special faint galaxies or something like that, right? So for that you need bigger telescope. So people started making telescopes bigger and bigger over many years. Of course, some people were making only lens telescopes, right? And they are the ones who finally reached the world's largest refracting telescope. Okay, lens, a telescope which uses a huge lens. And how huge is that lens? Let's see. Its diameter is 40 inches, or about 102 centimeters. Can you imagine how big 102 centimeters is? Any name for 100 centimeters? Any other name that you know? 100 centimeters? 1 meter, yes. Yeah. So sometimes people in science want to be very accurate, so they use very accurate measures. This is 102 centimeters, but yes, it's around a meter. So whose height is 1 meter here? Or whose height is 40 inches here? Anybody remembers your own height? I think most of you would be around 1 meter or so in height. So the lens here, just the lens is your height. Okay, so imagine that bigger lens. We have not even seen bigger than this size. Just imagine that bigger lens, but it is very costly to make, okay, and maintain. You have to maintain it. It should not get chipped. It should not get damaged. It should not get dust on it. It should not get prints on it. It should not sag. What does that mean? Do you know that glass is actually a fluid? Yes, so glass is actually a fluid, but it's a very dense and slow moving fluid. Okay, so if you keep a block of glass, say for 100 years, glass will actually flow down. Okay, and so the base of it will be thicker compared to the top. Yeah, so just imagine that happening to a telescope lens. We want a perfect size, shape, and I make a lens 100 years ago, and now it's bent out of shape, and I've spent so much money and effort making it. So that's a disadvantage, and we have to make corrections for that, and have to have measures ready. So the largest lens which was made was 40 inches or 102 centimeters, and it is used in this observatory in the USA called the Yerkes Observatory. In fact, it can still be used. It is perfectly working fine, but the telescope is quite old. It's from the last century, in fact. Okay, and its size is so big. You can see it's a 5-story building which hosts and houses the telescope. Right? Now, I'll just show you, compared to that, how big can you make refracting telescopes? Okay, so that is a reflecting telescope. You can make very big reflecting telescopes. So this dot that you see here, blue dot, is the 1 meter telescope. Okay, and compared to that, now these are a range of other reflecting telescopes that are either already existing or are being made. Okay, so just see how small it compares to the biggest refractor. Okay, so after this refractor, we move towards bigger reflecting telescopes, and one of the very important telescopes was a 100-inch telescope at Mount Wilson Observatory, California. And if you've heard of Hubble, okay, so you must have heard it in the context of Hubble Space Telescope. The Hubble Space Telescope is named after someone whose name was Edwin Hubble. Okay, and he discovered some important things about the universe, and of course they were discovered through observations of very faint galaxies, okay, over a long amount of time. And what did he do with these observations with this Hooker telescope, 100 inch at Mount Wilson Observatory, right? So that is the telescope which made this very significant discovery at the beginning of the last century. Okay, after a while they realized it is not enough. I want a bigger telescope. Okay, so that telescope was a single piece mirror, like the Newtonian that I showed you, right? The Newton kind of flat mirror, direction changing kind of mirror. Then they realized 100 is just not enough. I want more. Okay, and there are so many discoveries, like Hubble is making this groundbreaking discovery. I know what I can do with a mirror which is 2 times bigger. Okay, so 2 times bigger means the area becomes 4 times, right? So they wanted to go for more, and they made a bigger mirror, but then they knew that I cannot do a Newtonian type of design there. I need to make it compact. So they drilled a hole in between, and then of course, as I showed you, they used the Cassegrain type of design in that. Okay, and most of the telescopes, big telescopes after that, are kind of using that design. Okay, but again, this is a single block of glass, which is polished and mirrored to reflect the light from space. That was still 1940s, 1950s. Okay, after that we went to various kinds of techniques being tried out. So people said, why do I use one block mirror? Let me use several mirrors put together, but then their shape will be that of one mirror. Okay, so I'll use broken mirrors. However, all of them, the purpose is to focus light to one point. Okay, if they can serve that, I am happy. I don't care whether they are broken, they have lines on them or whatever. Yeah. So they started working on something called multi-segmented mirrors. So they have various segments which all together work as a brokenish mirror. But it's not to see my face and shave or put makeup. It's just to point light to one place, which is fine. Okay. So therefore, after that, people started making telescopes with various kinds of segments, and this was a big success. Keck telescope. Okay. So suddenly from 200 inches we could go to 10 meters. 10 meters, that's about 15 times my height. Okay, huge. That's 10 meters is, I don't know, 2 stories high, 2 or 3 stories high. Okay, that's just the diameter of the mirror itself. And on top of that, just imagine, that's just the mirror. Other than that, there is the whole paraphernalia, the tube, the enclosure, the other small mirrors, etc., the cameras which will be there at the back. All this is a huge system which was made. So what they did was they used these hexagonal kind of segments. Okay, so they make a blueprint, in which the whole mirror is designed, the shape required is designed, and then they break it into parts. And then that is given to a glass company to make. They deliver the pieces, polished and mirrored, and then they are put together at the location of the telescope in a proper way with motors, etc., to move them. So that happened, and so they thought, okay, if we are going to build one telescope, the design is the thing which takes the most cost, right? Once the design is made, you make one or two, it doesn't matter much. So the second one almost comes for free. So they, instead of making one, they said, okay, hey, so we have some extra money, let's make two and try out various fun things with them. So they actually made two telescopes, each of 10 meters. So it's combined width, if they were placed next to each other, is almost 20 meters, right? But ideally, each of them is a telescope, separate telescope of 10 meters in size. Just imagine where we have gone. We have gone from a 2-inch telescope, okay, let's say 5-centimeter telescope, to 10-meter telescope now, right? And that is 1990s. And of course, there were other people working on other telescopes, so they were just competing. I'll just come to that later. And there are now telescopes which are planned, which are even bigger. So this is, just see the change in sizes. I'm going to come to the details of these. See the change in size compared to this one, which used to be the largest telescope in the world when I was in school. Okay, and now we are planning for bigger telescopes and even bigger telescopes. And in the background, you can see this gray patch. That is the dream of an astronomer right now. There's no plan for such a telescope yet, but that's something people are dreaming of. Compare that to a basketball court or a tennis court. A tennis court could easily match this kind of size. A tennis court, right? Okay, so reflectors can be made big, and they can reflect a lot of light. So what do these telescopes see? I'll just quickly go to this slide. I don't know if it makes too much sense, but other than the normal light that we see, visible light that we see, okay, there are other things that are also can be called light. Okay, so you must have heard of ultraviolet light, infrared light. Okay, but then there are X-rays, gamma rays. There are also something called microwave, which we use at home. It's a kind of light, but a lower energy compared to what we see with our eyes. Then there are even lower energy light called radio waves that we see, which are used for communication. But these are all kinds of light. Yeah. So we are talking about only the visible kind of light. So just to make a point here and keep it floating in your mind, that there are other kinds of light which many other telescopes talk about. I am going to show you pictures of telescopes which actually deal with only optical or visible light, things which are visible to our eyes. Okay. So what can we see with the optical telescopes? We can see the sun, right? See the sun, and this is a nice image actually with a telescope, and you might be able to see interesting things like sunspots on the surface of the sun with a telescope. You can see stars, you can see star clusters, right? Lovely images. It's not just beautiful, there's a lot of information in it, right? So what is the information? Let me spend a minute here to see if you are attentive or you are curious enough to find some information from this picture, or get out some information from this picture. So let's see, what information can you give about this picture? So I'm showing you a beautiful picture, and I'm telling you it's a star. It's got stars, of course. That's very obvious. It's got many stars. That's very obvious. What more? And what can you infer from that? We also have a goodie bag. If you can give us a really good answer, then you get a goodie bag from the 30-meter telescope project. So let's see. Manjiri, can you give a goodie bag when somebody gives an answer? Thanks. Yeah.
Clear picture.
Clear picture, yeah. It's a very simple answer. I want something more Sherlock Holmes level, right? Zyada chamak rahe, kam chamak rahe, right? Again, simple answers. Yes, please.
Small particles of some planets float
Not really. These are just stars there. Yeah. Yes, sir. Yeah. Okay. So, well, that's you can see some pattern in them. So it's probably has a square pattern or a arrow pattern, as you say, right? That's again, I would say, a very simple answer. What is the important information other than, okay, I can form a square in that? That's very simple thing, right? It's based on, I want to form a square, you want to form an arrow, I want to form a tick mark. A more scientific information. Yes, please try. That's again, as I said, constellations is up to you, right? Where I see a scorpion, you can say it's a Ganesh ka murti or whatever. I mean, it's up to various cultures. I'm saying what is scientific information. See, scientific information does not change our culture. If I say they are blue, right? The name for blue will be different in French and Japanese and Spanish, but they will be meaning blue, right? That's in scientific information. I'm looking for such information. So please pay attention and think and give me an answer so you can get a goodie bag. Yes. Okay. Right. But what's the information you are giving me? This is something you are suggesting me to do. I'm asking for information, not suggestion. Sorry, no hard feelings. I'm just clearing my point that I want to make, and I'm just also clearing how you get the goodie bag. Okay, luminosities of the stars are different. Yes, somebody also said the same thing. That's right. Anything else? It's there. Some are small, some are big, some are bright, some are dim. Okay. This is not the orange belt. It's probably both of you have guessed. This is a star cluster in India. It is called Krittika. It's also called Pleiades in Latin or Greek name that it has. Krittika. Does anybody know somebody called Krittika? Yeah. So tell them they are actually a star cluster in the sky, right? And it can be seen in the sky. Right now, maybe not. A few months ago, it was pretty high, around 8 o'clock in the sky. Okay, I'll give you an answer, and then maybe in the next one you can give me some information, right? And I'll keep the goodie bag to myself. So look at it a little deeper. Can you see some wispy things, cloudy things around the stars? That's looking deeper than just the stars, right? So what do you think that wispy, cloudy thing is? It was taken on a cloudy night. Yes. अब किसी भी लैंग्वेज में बताइए प्लीज, कोई संकोच मत कीजिए. हाँ, नो प्रॉब्लम. तो आप टेलीस्कोप में गलती है या स्टार्स के वहीं पे कुछ हो रहा है? ओके. हाँ, टेलीस्कोप ठीक है. हाँ, वहाँ भी होता, सही कहा. That's actually a reason why you're seeing this wispy things. It is a reflection, of course. I mean, you see something because it's reflecting light. It's a correct answer. But what is it that is reflecting the light? So the light is being reflected by clouds. Okay. Yes, clouds. But which clouds? I won't take out a telescope and try to look at the sky and use my precious time on a cloudy night. So it's not clouds in our sky. These are gas clouds at that place where the stars are. Okay, just imagine. Now these clouds are not small clouds like the ones in our atmosphere. These clouds are bigger than solar systems. These are bigger than solar systems, not just one system. They're bigger than solar systems. So if all of these stars, let's say, have a solar system, this cloud is as big as this, right? Now just imagine that. And that is a star cluster. Another question people asked, so where does this cloud come from? So first, when you see with the naked eye, you just see some stars, like you said, a pattern, arrow pattern or something like that. You see a constellation. Then when you look at with a telescope, you'll see, okay, it's a pattern which has mostly blue stars. Okay. And then you take a bigger telescope, and then you see these wispy, cloudy things there, right? That's how your knowledge increases, right? Then you know, oh, there's something more there. I didn't know of this. So then it leads you to a question, two questions. One, where did these stars come from? And then you say, why is this cloud there? Then people join these two together. They know what the stars are made up of. Very good. Stars are made up of hydrogen gas. And this is hydrogen gas. All these clouds are mostly hydrogen gas, right? So there's a direct relation. Where did the stars get their hydrogen from? From these clouds, right? So essentially, we are now tracing back the history of these stars, right? Without even having to actually see them being born or something. So what I can from this deduce is that at some point it was more gas than stars, and they have formed there. Okay? And since in this patch of the sky there was so much hydrogen gas, more stars formed there, and that's why they cluster together. In our solar neighborhood near our sun, there's very little hydrogen gas. I don't see clouds around our solar system, right? So there's no hydrogen gas there, and so it's obvious that our star was formed alone. Okay? So it finished off all the gas in our cloud, and it formed alone. However, if we were unlucky or lucky, I don't know, to be in such a cluster, we would have so many suns in our sky. Right? So I'm talking about going to that level of information when you're looking at a picture. That's what an astronomer has to do, right? So when they look at a picture, they have to get as much information as possible from it. Like अभी गर्मी के दिन है तो गन्ने का जूस हम पीते हैं, तो गन्ने में से कितना जूस निकालते हैं आपको पता है, इसको 5 बार 6 बार डाल के सारा जूस निकालते हैं. That's how astronomers use their information from the pictures that they take. They got as much information as possible. So this is a star cluster. So you can see stars, you can see star clusters. In fact, you can see places where stars are born. Now what is this? It's also called a ring nebula because it looks like a lovely little ring. Any idea? And how is it different from the previous one? I'm sorry? Lots of gas, okay. Because of not sun rays, but not sun rays. Anything else you want to say? There's something particular here which is very different from the previous one. Yes, please. I don't think you can get that information directly from this. So I'm just saying from this, what can you tell this picture? But it's not so. I mean, it's actually not. It's the other way of what you're saying. Yeah. Okay. No, not really. Sorry. Yes. No, gravity is not important here right now. Yes, sir. It is also not the refraction. It is all emission of light. It's giving out light. Reflection is still, yeah. Sorry. Refraction. Yeah. So Vivgyo. Sorry, it's not even refraction. It's all actually giving out light of various colors. Yes, back there somebody wants to say something. Sorry if I'm putting really difficult questions to you. There'll be simpler ones later if you don't mind. You have something to say? All right. Okay. So let me tell you. So this is a nebula. Nebula is a gas cloud. Okay. So that's one thing that is clear. Here, the gas was diffused, randomly placed everywhere. There was no shape, irregular. Here it's regular, it's in a circular shape. In fact, it's called a ring because it's like a ring, circular ring, right? And you can see there's an inner ring, there's an outer ring, and inside also all the colors are within circles, right? So it is therefore not a random event. It's not like there was just gas everywhere and something formed here. This is the formation of this has some other cause, okay? And the cause in this case is opposite of what you said. It's actually the remaining part of a star which got exploded. Okay, so stars, in the last slide I showed you stars which were forming at near a gas cloud. Okay, of course they form, they spend billions of years there, they don't move around and go to foreign countries, they stay there, they spend their lives just giving out light from their insides. And particularly big stars, okay, they have I mean all different kinds of sizes and masses of stars have different ends. Their end of life is quite different depending on what their mass is. The bigger ones, they end up in something called a huge explosion, which is called a supernova explosion. Okay, an explosion in which the inner core, the most inside core, goes compressed and the outer parts go outward. They are exploded out, okay, thrown outward, right? And of course, since it's a spherical star, when the explosion happens in all directions, everything goes out in a symmetric way. It's in a nice spread out way, right? So that's what makes a nebula, which is like this, okay? And in fact, you can see the remaining part of the core here. So this tiny dot, that's at exactly at the center of the circle. So that's the remaining part of the core. Of course, I am not saying that you all should know this right from the beginning, otherwise this talk is not necessary. Yeah. So, but this is something people again inferred. So people looked at this with a big telescope and they saw, hey, what is this? And why are there so many colors? Then they analyzed these colors. In fact, colors can tell you about what kind of elements are there. Okay. And if any of you have done flame test in a chemistry lab, the children should look up to these lovely tests that are there. Then these, the flame color actually tells you what salt it is, right? In science labs. Right? This is actually being applied here. There you must have just learnt it and written it down. It's actually applied. So you say, okay, fine, it's probably the gases here are not the same ones that you encounter in chemistry labs. But if you see, say, oxygen, okay, oxygen, if it's really heated up, it gives you a bluish green color. So therefore, you can see that this part has some presence of oxygen gas. I'm not saying it's as abundant as on Earth, but there is some oxygen gas that you can find there. Nitrogen has a particular color. If it's really hot, it emits at a particular color. Okay, there's various kinds of other things, including carbon, silicon, and all these elements, when they're pretty hot, they emit at various colors. Okay, and this can also be seen by telescopes, and this kind of information is also available to us. So what we saw in the previous picture, if you do that analysis, we see only hydrogen. Here we see hydrogen, helium, all these other gases, silicon also. Okay, and from that we know there are more elements there, and these elements, they do not form so easily. They need a violent reaction to form. Okay, just you cannot take 2 hydrogen and say become helium like this. Okay, they need the kind of pressure and temperature inside the sun's core to form helium, right? And to form for this helium actually can combine to form, let's say, oxygen, carbon, nitrogen also, but the conditions need to be really bad, really extreme, and these can only be found inside stars, inside big stars. So if we find these, we know there was a old big star here. Okay, and now we actually see it has exploded and formed this, and therefore so much information has suddenly come to us about the end stage of a star. Okay, without we actually having to see an end stage. Of course, we can also see them, but they happen suddenly. So it's not that a telescope will be pointing at that time always. But here, this nebula exists for billions of years. Okay, and it will slowly change. You can also see the changing way. So you can see the sun, you can see stars, you can see beginning of stars, you can see ends of stars with telescopes. optical telescopes. And then you can see bigger clusters of stars which are called galaxies, okay, and these are huge collection, and this is our closest big galaxy, Andromeda Galaxy, okay, also called Devyani in India. This one has around 100 billion stars, 100 billion. Okay, so we are just 6 billion people on the world, on the earth. So every person will have more than our number of stars in this galaxy, right? If you want to go and own this galaxy. So, but it's pretty far away, and with our eyes, it's a very faint wisp in the sky. Other galaxies we can't even see, but this is our closest galaxy, so we can just about make out that this galaxy is there in the sky, Andromeda. Okay, but with the telescope, see the sharpness, see the what is called resolution, see the details that you can see, right? And this is still not an image which is taken with the best telescopes in the world, right? And the best planned telescopes are still to come. Okay, so that's what I'm going to take you to now. So what are the best telescopes in the world today? What is this world of large telescopes that I started with? I'm now going into all these records kind of a thing. So I told you area is important. The more light you collect, the brighter you can make the object look, and the sharper the image will be. These are two advantages of a bigger size of a telescope. Okay, so this is kind of the largest area used by any telescope. So this telescope is called GTC Gran Telescopio Canarias, and it is on the Canary Islands in Spain, a place which is actually an island in the Mediterranean Ocean, okay, and far away from any city lights, etc. And the area used here by this is the largest. It's the diameter of the telescope is 10.4 meter. What do I mean by that? What do I mean when I say 10.4 meter diameter? Sorry? The mirror, because we stop lenses at 1 meter. So the mirror, it's a segmented mirror, but it's 10.4 meters across if you take a look inside. So that's one. Then there are the Keck telescopes, which are around 10 meters, 2 units of 10 meters. This is a top view at a place called Mauna Kea. I'll just describe that to you. So these are two. You can see inside now. Okay, these are the mirrors. Then of course, if that is 10 meters, then you can see the enclosure itself is around 30 meters in size, and it's huge. There are two of them, and this is a building actually. There's a lot of offices in here. There's actually a truck standing here. Okay, so you can compare the size of that. These are the biggest telescopes. They are nothing. They are not biggest, largest, anything. There are no records on them now. But for almost 15 years, they were the biggest telescopes in the world for me. So I just kept the picture. Then there's also the very large telescope, another forerunner for a record, but it's got 8.2 meter class, 4 units. Okay, 4 units. Each has a mirror, 8.2 meters. So if you combine their length, it's quite big, right? This is one of the more important telescopes in the world, VLT, very large telescopes. Astronomers are very imaginative in giving names to telescopes. So you can see very large telescope. Okay. Next, we come to a very imaginative name, a large binocular telescope. Can you guess what it does? It's a large binocular. So it's, of course, it doesn't use lenses. It uses 2 telescopes, 8.4 meters, both looking in the same direction. Okay. So we just hoping that this would give some more information compared to just having one looking in that direction, right? So our eyes, you know that it gives you stereoscopic information, right? Because I can also find out depth because I have 2 eyes on the side, right? You can try, doing things which require a measure of depth with just 1 eye, and you'll see you'll be not so successful, right? But 2 eyes give you this sense of depth. So this is one which we are trying to use. Also, it gives you a wider angle in which you can look. So 2 being here. So if both the images are taken on the same camera, then you can get a wider coverage. So you can cover more part of the sky at the same time with the same telescope. Right? They use the same motor, so everything is moving together, and they are covering a bigger part of the sky. So that's the largest binocular telescope. It's in Arizona, USA. Again, a very dark place. Then we have the largest solar telescope. This is a telescope which looks at the sun especially. It's a very different one from the other telescopes. In this, the diameter is not the most important. It's how complex it is and how it reduces the light of the sun and how sharp the images are. Okay? Of course, in that also they have tried to make a 1.5 meter diameter telescope, which is particularly used only in the daytime, just to see the sun. Okay? And so the light comes here, and then it's passed through a huge tunnel down here inside an observatory place, where it is kept cold because you're collecting so much light. I told you this much of a magnifying glass can burn your paper. Now you're trying to focus the sun with a 1.5 meter mirror. So that's a very difficult thing. So it's got to be a more complex thing, and there's a lot of cooling, etc. involved. And finally, at the end, you can actually see the sun's image like this big on a table. So you can just see, okay, you don't even have to look with your eye. Yeah. It just comes on your work table, that image. Lovely way it works. Then we have the Southern African Large Telescope. It has the largest mirror dimension. Now, record करना है तो कुछ ना कुछ अलग-अलग लगाएंगे. So we say area ज़्यादा है, diameter ज़्यादा है. बोलेंगे एक साइड में diameter ज़्यादा है, दूसरे में कम रखेंगे, but एक साइड में थोड़ा ज़्यादा करेंगे. Of course, they don't do it for records. There are technical reasons why this telescope has 11 meters on one side and 10 meters on one side. So it's like an oval, slightly right, little bit oval shape. But then record-wise, this has the largest mirror dimension of 11 meters. Southern African Large Telescope. Very imaginative name, where the short form is SALT. So, another nice picture at night. Why I'm telling you about this telescope particularly is because India is a partner in this. Okay? This is based in South Africa, but India has a share in this. About 10% share is Indian, and therefore Indian astronomers get a 10% share of the time which is spent on observing the sky. Okay? That's a really important thing to realize. This is a twin of the SALT telescope made with similar technology, the Hobby Eberly telescope, and this one I'll particularly show you inside of it. So you must have been wondering, how does it look for real? So this is how it looks. So this is the whole telescope, and you can see this shiny mirror, huge mirror, and there are people standing here. There's a person here, they're discussing over coffee, tea, or whatever, right? So almost every mirror segment is almost the size of a person. Right? And so on this side it is 11 meters, on this side it is 10 meters. Right? So it's amazing. I could keep looking at this picture for a long time. Yeah. Okay, so these are huge things. They are not so easy to make. In fact, sometimes not just one country can make a large telescope. It's costly also, and nobody wants to give money to science anyway. So we have to resort to partnerships and get these things made so that science can progress. Well, the process of making a telescope is not just an astronomer saying, "Oh, I want to study stars." It's got a lot of detailing, right? So we put together all sorts of heads. There are engineers. There are engineers of different kinds: civil, electrical, mechanical, computers. Everybody comes together, and of course, the process of actually making a telescope starts with the construction. And of course, you have to find a site which is really dark and far away from human intervention, right? So this is the time when the very large telescope that I showed you was being built. So this is one of the units being constructed, and so it goes through the same construction kind of things which you see happening in the city, which makes the skyline ugly with cranes and things like that. So, but then the finished product is really good. You can see, and in fact, this whole site had to be first found. And this place in Chile is 700 kilometers from the closest city. 700 kilometers from the closest city. So just imagine having that in India. It's not possible, right? 700 kilometers to kuch nahi hai. In all directions. Right? So they had to make a road first and then get there. So yeah, so in a cartoon way, you find a site first, then you reach there first just to survey it. So you have to make roads to various places. You travel across barren land and find a place which is good. This hill seems to be good. So we try to make things which are at a higher level so that there's less atmosphere between us and the sky and the space. Then we have to, of course, make it leveled. So all that takes a lot of engineering work. Then the dome construction starts, the base, the enclosure itself is made. Because we can't put the mirror without the enclosure being there. It will get dirty, right? So we have to make that. Then things are transferred there. And then finally, this is a planned construction of a telescope. Then finally, we come across a really, really giant telescope, large telescope that we are, this one is particularly the largest planned telescope whose diameter would be about 40 meters. 39 is currently the one which is being planned, okay? This is again very imaginatively called the European Extremely Large Telescope. It's made by the European Space Organization, European Southern Observatory, ESO, not ESA. In the same, in a place close by to the VLT, the Very Large Telescope, in the southern country of Chile. Okay, it's going to be huge, and in fact, if you compare it with small 787, this is how big it is. This one can actually sit inside it, right? It's going to be that large, extremely large telescope. But this is going to be in the southern hemisphere, right? For the northern hemisphere, we have the 30-meter telescope coming up, and that is the project which is also sponsoring me to be standing here and giving this talk. It is going to be at Mauna Kea in Hawaii Islands, on the Hawaii Islands in the USA. Okay, this very imaginatively tells you that it is a telescope whose diameter is 30 meters big. Okay, and so I mean 30 meters is kind of a medium step between 10 meters and 100 meters. Okay, intermediate step. We don't suddenly want to jump steps which are too big for us and too beyond our capacity and technology today, right? So 30-40 meters is what we are right now planning for, and hopefully the next generation after this succeeds, we can try for 100 meter, but that's going to be a really big challenge. 100 meters is not so easy to handle and it is required to be at the best site in the world also, which has to be the most remote site, right? So there's a different level of challenge. But this is pretty good design, and it's being made at a place which is quite tried and tested. 13 international observatories already exist on the peak of this big mountain called Mauna Kea. It's so high. It's 4 kilometers high. The top is 4 kilometers above sea level, right? So it's half the way to Mount Everest. And on top of that, 13 international telescopes already exist. These are the two Keck telescopes which also exist there. This is the Subaru telescope. Oh, sorry. I think, no, this is, yeah, this is one of the other countries who run the telescope. And this is ice, right? So it's almost always frozen up there. And what you see beyond here are clouds. So it's way above 2 layers of clouds, in fact, not just one layer. So there's something called inversion layers, and it's beyond the second inversion layer, 4 kilometers high. So there's hardly any disturbance, and we get clear nights. Even if it's raining down there on the island, there it's clear, right? That's the best site in the world to do astronomy. The second best site is, of course, in Chile at Paranal, where the VLT is there, very large telescope, and it is pretty far off. And that is one of the nice reasons to join astronomy, because we always get to go to exotic, faraway places where people don't usually go. Right? So if you like that, this is your field. Now you'll notice that there's something coming out of the telescope here. Right? This is strange because the telescope should be looking at light, not giving out light. Right? So this yellow, and it's yellow. You see another picture of Hobby Hyperly telescope, even the previous one, you would have noticed that this is a light coming out like this, right? So that is a laser beam, right? And it is being used for a process called adaptive optics. Now, what happens in the sky after we build these lovely telescopes at some remote places, etc., far away from human light, we still don't get clear images. And this is because of the atmosphere between us and space. Right? There's a layer of atmosphere. For us, it is clean, clear. There's nothing happening. But if you look at images of stars, they're most of the time twinkling. Right? For us, that's a beautiful thing. We write poems about it. But for an astronomer, that's a nuisance because they want the perfect image, right? If I showed you that star cluster and all the stars were moving all the time, you'll probably get no information out of them, right? So what they may look beautiful, but the information will not be so useful. So what an astronomer wants is every dot of light that comes to them should be fixed at a point and it should give me a steady image. Okay, but that doesn't happen because the air in between is changing constantly, right? So what astronomers do is they try to cancel that effect. Okay. How do you cancel? You can't stop the air from moving. What we do is we check for what is the change in the air from here till the edge of space, and we change our telescope accordingly. What does that mean? Right. I was telling you about focusing. Right. It's telling you that the light has to be focused to a point, so I then adjust my lenses so that the point gets focused, right? So that has to be done all the time and repeatedly because the air is changing all the time. So what we do is we make a star in the sky. How do we do that? So that's where this laser comes into play. So this is something called this is a particular color of laser, and we know that from meteorologists, we also partner with other scientists. So from meteorologists, we know that there's a layer of ions at some level in the sky, which is made up of sodium ions, right? And if any of you know sodium lamps on the streets, what color are they? Yellowish, yes. So sodium ions, sodium gas, when excited, gives out yellowish color. Okay, and if we actually put yellow strong beams of yellow lasers on them, they twinkle. They basically give out light. So the rest of the ions will not give out light, but a laser focused on a certain ion, let's say, or a few ions, will make them absorb and give out the light back to you. Okay, so this particular phenomenon is used. So what we do is we shine a laser on them, they get excited, they absorb the light, and then they send it back. But they don't send it like this, they send it everywhere. So it looks like as there's a new star has formed there, right? But it's a star which we have made, because we have pointed a laser we wanted to point a laser exactly to that point which we fixed, right? And that point is close to what we want to see, the other stars, other galaxies, etc. Now if that point is not seen at where we want it to be, it means the air has changed and moved it slightly. Right? So if I say it's at this place, but it is, and I take a picture of that area, and it's not at that place, it's moved slightly. So I know that all the things in that frame have also moved slightly. Right? So what I then do is I change the shape of my mirror to focus that so that they come back to the same place. Okay, and this is done repeatedly. It's done quickly as soon as I get a change. So there are computers and software running all the time who do these calculations, and then they pass on information to the telescopes, the mirror. And the mirror being segmented, there's small pieces which make up the mirror. This is an advantage now, because changing the whole mirror would be a very difficult thing. Here we have small pieces, so I can just tell, okay, piece 3, 5, 7, just change a bit. Okay, so this is called adaptive optics. So we adapt to changes in the atmosphere, and then we can get much better images. In fact, how better? So a regular this is a simulation, of course, but a regular telescope without adaptive optics can, if it was giving such an image, with adaptive optics, you might be able to see things so clearly. Okay. It's the simulation on atmospheric effects that we have done. So which one would you prefer? So obviously the latter one, and that is why we invest in adaptive optics technology. So now this 30-meter telescope that I was talking about, so it's not just a big telescope, multi-segmented telescope, it also has adaptive optics technology built into it right from the beginning. So it's not an add-on ki baad mein zarurat padi to use kiya. It's right from the beginning we are building it, and you will get to know about all these things and more information about which parts of this adaptive optics system, of the base of the mirrors, etc., are being made in India. And some of the mirror telescopes, mirror segments are being made in India. Okay, so that's a big contribution that India has to this particular telescope, the 30-meter telescope, and that's why I would like you to visit the pavilion, the exhibition pavilion, if you have not already done that, and get more information on the project itself. Okay, so here I wanted to tell you about what are the advantages and what is in general the world of large telescopes, how they function, how exciting how exciting is the stuff that they look at, observe. But then there is also stuff which they may not have seen before. Okay. If you do not build bigger and better instruments, there might be things which you have not seen before, and we've seen that. I mean, we've gotten rid of the atmosphere at some time. We thought, let's send a telescope to space, and we did. Okay. So lots of people said, why are you spending so much money sending us telescopes to space? This obviously is the Hubble Space Telescope. Its size is only 2 meters. The diameter is about 2 meters in size. Okay. They say, I can build a 10-meter telescope on the Earth at this cost, because going to space is very costly. Right? They said, no, let's go to space, try it out. And it did, and it has given us a revolutionary it made a revolutionary change in the way we see things. The kind of knowledge that we have of the universe has amazingly changed in the last 25 years since it's been there, right? So if we don't make these things, we will make sure that our future is very dull, right? We just stay stagnated at our information level. We have to make these, and so therefore I'm very happy to introduce you to the exhibition, which actually showcases all the big steps that the world is taking and what is the Indian contribution in that, right? So please do visit the exhibition. We will be happy. We have a lot of volunteers, enthusiastic volunteers trained and waiting there to give you more and more information about it. And of course, we'll keep having these informative talks and lovely stage shows like the one at 2 p.m. today about optics. So please do come back. And of course, if you're interested in astronomy particularly, they're not all astronomy projects, but if you're interested in astronomy particularly, keep looking up. Thank you. This is the lecture. Do you have any queries, any questions to ask? Yes. Of course, yes. Yeah. So all sharing means, partnership means we get share in the time. That's the most important thing we ask for in any telescope. For general public, I would say no, but why? Because an hour of, let's say, using the Keck telescope here costs you close to, I don't know, thousands of dollars, because the whole observatory has to be running and everything has to be run on precision stuff. Also, the cost is there. You've made the whole thing, so you distribute the cost in time, and so every hour costs something, right? So also, there's a limited amount of time of clear skies during the year, etc., which we don't want to waste, right? So we do focused observations, and people have to. It's not that all scientists can use it also. So the people have to actually compete with each other. They have to write proposals saying, I want to see this particular thing and want to, study this particular galaxy or this particular kind of light from this particular source, and then that has to go through a competition of people proposals are reviewed, and then some of them are selected and given time. So now even amongst astronomers there's a competition. But it's not like we want to close things out to public. You cannot see through these with your eye. So you'll anyways be seeing an image, right? So any big telescope, there's no eyepiece there. There's no eyepiece for telescopes. They're all cameras. We want to use each second of it and record whatever it sees. Then you see it on your screen. So most telescopes are making their data public. What does it mean? Whatever they have collected, whatever pictures they have taken are being put on public archives. So each telescope has their own website where you can see public pictures. Especially Hubble Space Telescope has been such a wonderful project which has released so many beautiful images. Even if you don't appreciate the science or in-depth observation, it's just beautiful images to see. So yes, all projects are giving out images and data to the public. However, even astronomers don't get to see through them like that. India मध्ये आहेत काही. I can just show you some pictures. एक second. So India also has a lot of telescopes, including the Vainu Bappu telescope, which was at some time, let's say 50-60 years ago, the largest telescope in Asia, built and designed by Vainu Bappu, Professor Vainu Bappu, who is called the father of modern astronomy in India. He is the one who brought modern astronomies and astronomy observatories to India. So it's in Tamil Nadu. Kavalur. Yeah, Kavalur is the exact name of the place. Then we have another observatory. It's much bigger now in Ladakh, Leh, called the Hanle Chandra Observatory. Okay, this is another 2-meter class telescope, and so it's at one of the coolest and driest places in the world, Ladakh, and gives us great results. Again, this is controlled from Bangalore via satellite. This can be, I mean, there's a person there, of course, but so we are also at that forefront of technology where we are able to build our own telescopes, and now we are sharing workload of major international projects so that we can get experience. Our science students can get chances in the future to use such telescopes. Our engineering students now can get chances to be part of such projects, and our companies, they get expertise in technology and experience in making world-class things. We are really struggling to tell Indian companies that, see, this kind of precision is needed, this kind of finesse is needed, quality control is needed, and now they have realized and they've come up to that place. And this has been a big step. So yeah, we have observatories in India. I particularly would like to show the observatory which is run by IUCA, the Inter-University Center for Astronomy and Astrophysics in Pune. I work there. So this is another 2-meter class telescope. It's close to Pune. You had a question? Yeah. All right. Okay. So perfectly. Okay, I will direct you to the demo corner where we have our team waiting which can advise you about which telescopes to buy, where to buy, for which age group, and what kind of interest range you can buy them. So I will suggest that you go there. Sorry? It is in the science center. You go back from here to the science center main building where there are many dinosaurs. So inside there on the right hand, there's a corner called the demo corner, where you'll see our team there. Okay. So all of you are welcome to go there and see those demos also. Yes. Okay. No. So what she has made is a spectroscope, not a telescope, right? So that is actually giving you a spectrum. Okay. So spectrum, what is spectrum? Is it like I told you, a prism, when you pass white light through it, it can disperse into 7 colors. Those 7 colors are called the spectrum. So any light, if it's dispersed into component colors, that's called a spectrum. So what you're seeing is the spectrum of the sunlight. So it's not the ring nebula, it's the sun's own colors. Yeah. Sorry? Which thing? Yes, this talk will be there at 10 to 11 every day. Yeah. All right. So I think we started a little late, and we are also ahead of, not ahead, we are beyond the time. But I will still not deprive you of some of the goodie bags that we have here to give away. So I'll in general ask a few questions. They'll not be as hard as the last one. And it's a tiny quiz. Please put up your hands, we'll come to you and you give your answer. And if it's right, you'll get a goodie bag. So, Manjari, can you come here? Okay, so I just showed you so many telescopes. So, can anybody tell me which is the telescope that uses the largest area? Don't look at notes. Anybody, which is the telescope which uses the largest area? No. No. What is the name? Okay. Sorry? No, that is still planned. It's not yet made. Okay, Canary Islands. Please give him a bag. Thank you for coming. And okay, which is the, now you have to tell me the name, right? Which is the telescope in which India has a 10% partnership, and it's already made. So India has partnership in many telescopes. Which is the one which is already made, and India has a kind of 7 to 10%. I don't know exactly the distinct percentage. Oh. Okay, you raised your hand first, so please tell me the full name, and I can give you the. Can you tell me the correct name of it? So whoever tells me the exact correct name without looking at notes will get the prize. Okay, Southern African Large Telescope. So why? Because it's not South African. South Africa is a country. It is a telescope which is a partnership of Southern African countries and India, and maybe Canada. Something like that. All right. So. Let me see. Okay, so which is the second best site for astronomy studies in the world? Second best site. So let's. Can you tell me the exact name of the place? So you've got your chance. So let's give others a chance. Can you tell me the exact name of the area at least? Chile is a whole big country. It has got cities and people. Paranal. Yes. So one goodie back there. Thank you. Okay, and so tell me, you have to give both these answers correctly. What are the two important technologies or important features, technological features, which make the 30-meter telescope special? Two important technologies that it uses, the features that it has. My God, we have digital assistants these days. So that's the last question. If you can tell me, if you do not know the answer, please go to the exhibition and find out. But I have given the answer in the thing. So I've described to you two kinds of things which put the modern large telescopes aside from the ones 30 30 years ago. You want to try? Optical what? Okay, diameter. Sorry? Sodium ions light. Yes, can you tell me the technology name? This is a quiz, so I have to be a little. Yes? It's not called laser technology. Laser technology is like I am using this is laser technology. So, yes, ma'am, there. Okay, and one more. So there are two features which it has, and one I described earlier, one I described earlier in the talk, one I described later. It's there are. It's not yet made, so it's then there are 13 other things which are there. So it's not the unique thing. So adaptive optics, you get half a goodie bag yet. So like this, and behind it is the logo of the Indian partnership. So India has a coordination committee which controls the partnership of the Indian astronomers, scientists, engineers, companies, etc. in the 30-meter telescope. So here's the logo of both, and what's inside? There's a pad, and there's a nice badge that you can wear here. Last, it's simple. I've actually told you. You'll say, oh, why didn't I say that? But it is very important. It's what about TMT? What is the other special thing? One is adaptive optics. You're saying mirror, but kya hai? What is that? Okay, you said it first. Fine. So, yeah, I have to do that. So, lady there and the lady here gets the bags. Yes, segmented mirror technology and adaptive optics. These are two things which are inbuilt right from the beginning, and which sets this telescope apart. And of course, there are many other things which are very, very unique, but they are not very easy to describe at this place. But these are two definitely important things which scientists have put into this telescope right from the beginning. Earlier, they were not. They were more of an addition, right? And I'm happy that Indian astronomers, engineers, etc. have put together this head, and they are now one of the leading technology developers for adaptive optics from India. So yes, there's a big future, and I hope you find out much more from the exhibition about all these things. Yeah. Of course, we can divulge these names. Everything is to be, we don't want RTIs. There's a list of, I think, 30 companies and institutes. Again, at the exhibition, there's a list with the placing of them all over India. So they are from South India, North India, East, West. Several countries, several companies. Small, big things like companies like Godrej, L&T, and there are small companies like Avsarla from Pondicherry. Nobody knows of them also. There are all sorts. All right, so thank you for being here. Thank you for all the fun we had. Lovely audience. I request you, whoever wants to know about making small telescope, low-cost telescopes, please find our team at the demo corner in the Science Center, and they will be there mostly throughout the week. Our talks will be here at 10 every day morning, so we'll try to start at 10. Then the road show, the stage show here with Galileo on stage will be at 2 p.m. and that will have optics demos. It will not be as high fundu probably, but it will be interesting, and kids can also enjoy that. So please make sure, if you know any young students, school students, if you're part of any teacher parent group or something like that, just forward this to people saying that there's a stage show here at 2 p.m. So that's all the announcements we have. Please enjoy your day. Thank you very much.